Okay. So today I want to do something different from what we ended with last time. Namely, last time we were looking at the adjoint of a linear map from a finite dimensional inner product space to itself over R or C, of course. Right? And so here are two parts, the relevant parts of that theorem or proposition. Okay, stated the proposition and proved it. Yeah, and the proposition that first of all we needed to prove the following: if you have any finite dimensional inner product space, then you can look at this map, capital Phi, Greek letter, sending V to V star, sending a vector V naught to the inner product against V naught. Now, because this is linear in the second argument, therefore every such map is indeed in V star. Right? And the claim was that this is a conjugate linear bijection or isomorphism. That we proved last time. And then using this, we prove that there exists a linear map, a unique linear map. So given a T linear map, there is a unique T star such that this happens. Okay, this satisfies it. And using this, then we looked at the matrix of T and T star with respect to some orthonormal basis of V, and said that look, the matrix of T star is the conjugate transpose of the matrix of T. Right? And because of that, and because we call T star the adjoint, we said now we can define the adjoint of any, not just square matrix, but a rectangular matrix. Right? Now, because it's a rectangular matrix, of course, you should ask then, is there an analog of the adjoint of a rectangular linear map, meaning a linear map between two different inner product spaces, which are both finite dimensional? The answer turns out to be yes. And so this is already proved. Let me start by changing this slightly and proving the general statement. And then we will get to the adjoint of a general rectangular map and continue. Okay, so let's do this. So yeah, so let me just state this more completely. So I will change this completely. So now let's. So the new statement, maybe I should write it in black. That's this one. So proposition part 1. Right, so this is just the part 1 part. So part 3 doesn't have a V and a W. It just has V and V star. So that part is unchanged. Part 1 is what changes. So here again, say V is a finite dimensional inner product space. But now because I'm going to take another inner product, let me put a V here. So this is the inner product in V. Is finite dimensional. And W is also an inner product space. And so I put a W here to denote the inner product in W. That's different from the one in V. Okay, is an inner product space. Is also, sorry. Maybe I'll put it this way. Say V and W are inner product spaces. Are inner product spaces. Again, over of course F, which is either reals or complex, and the dimension of V is finite. Okay? Given a T, given a linear map T, there is a unique T star. There exists a unique T star going the other way from W to V, such that the same equation that I have written and erased, but V prime should be replaced by W. So such that, let's write this down. So T star W. So T star W is an element of V because T star goes to V. And so therefore this is an inner product in V. And this is equal to W comma TV. And this inner product is in W because T of V is in W for all V in V and W in W. Okay? And here you see I don't need W to be finite dimensional, only V. That's the statement. Okay? Okay, great. So let us prove this. So let us start by proving this, and then we will move on to the adjoint of a general rectangular map and so on. Or the matrix of, we can then talk about the matrix of this T star with respect to orthonormal bases For that result, we will require the dimension of W to also be finite. But for this result, we don't. Okay, so let's do this. So yeah. So the proof is exactly the same proof, but as for V that I did last time, but let me repeat this same proof for W. So given any element W, I want to define T star of W. That's what I want to do. So first of all, consider the composite map. As I said, it's the same proof. Composite map, which takes a vector V in V. Okay. First of all, you take it to TV. So this goes to W. And then you take it to the inner product against W. Just like this here in W. And so that means this goes to the scalars. This you can check is clearly a linear map because you see it's linear in the T is linear and W against something, as we already said, all these are linear maps. So the whole composite is a linear map. This is a map in F star, this. And where is it going? It's taking V to F. This is linear and goes from V to F, or let's say this is linear from V to F, i.e. in V star. And V was finite dimensional. I don't care about W. V was finite dimensional, but therefore I can use the previous part 3. So at part 3, it is equal to, so by 3, it equals phi of some V naught tilde. Let's call it V naught tilde, as I did last time, just to keep the same proof. Okay, for some V naught tilde in V. So now define. Sorry, for not just some, for a unique V naught tilde in V. Right? Because that's the whole point. It's a bijection. So V star is in bijection with these guys. There's a unique V naught tilde. So there's a unique definition. Define T star of W to be V naught tilde. That is the case. Now clearly this is well defined. Okay. And moreover, let's check. So I think these were what I had said first. T star is well defined. We need to check all these things. It's well defined, it satisfies this property, it's linear, and it is there exists. The existence part is done. This is the exists part. There are 3 others, right? There's a uniqueness part, there's this property part, and there is the linearity part. Okay, so let's check. So okay, the second part, all this exactly is identical to last time. That's it. The proof is the same. Okay, so let's write down. So T star W comma V. And this is the inner product in V. Now what is T star W? T star W is V naught tilde. But but what is V naught tilde against anything is literally phi V naught tilde of V. And phi V naught tilde is the composite map here, right? So phi V naught tilde of V is W comma T by definition. And of course that inner product is in W. So okay, so that proves this property. And this is true for all V and W. I won't say V there and W there. This is clearly true for all V and W. Okay, that's part B. Part C is the linearity part, and part D is uniqueness. So maybe I'll do uniqueness here because it's smaller to fit in. I'm just saying, I can say part C is uniqueness, but because last time I said part D was uniqueness. So I'll do it here. So say uniqueness. So there exists, this is the property, this property here. This is the uniqueness. And then there's the linearity part. So the uniqueness is, suppose T1 and T2 are 2 linear transformations satisfying this property. Say T1 and T2 belongs to lane. This is why it's part D, because first part C I need to prove that it's linear. And then suppose there's any other linear map satisfy this equation check. Okay, for all v w. See? Then you can write this down. You can say that let's see. Let me say I said this last time, but fine. T1 of w minus t or comma v. Let's call them T1 star and T2 star. T1 star of w comma v equals w comma tv. But the same thing also equals by the same equation check. The same equation check. This also equals T2 star of w comma v. And this is true for all v. And also for all w, of course. But what happens now? Then you can subtract the first term on the left hand side and the right hand side, and you get 0. And so what we get is that, i.e., T1 star of w minus T2 star of w, comma v is 0 for all v. So by the homework problem, the same homework 12, I think, if some vector is orthogonal to all of v, then that vector is 0. So T1 star, and if that vector is 0, then T1 star of w is T2 star of w for all w. So this is again, remember, this is all v in v and all w in w. So this is true for all w. So these two functions are equal on all of w. So the functions are equal. Okay. And finally, the linear part. So how do you prove linearity? Well, I have this T star, it's unique map. So all you have to prove is T star of W1 plus CW2. Okay? And I have to prove that this is equal to the vector. Remember, this is a vector in V. Okay? And I have to prove this is equal to T star W1 plus C times T star W2. Now, how do you prove two vectors in an inner product space are equal? It's enough to say that if and only if their difference is 0. How do you prove a vector, the difference vector is 0? It's 0 if and only if it's 0 against any vector in V. So that's all that we do. So take any V in V and compute this. This should all be in V. This is in V. This is in W. And this is in V. I'm just putting in all the inner products where they should be. So, okay, so now how do you check this? So just evaluate this thing. And this is the last thing. Once you evaluate that, you get 0. This will finish the entire of this proof, right? There exists a unique linear map which satisfies this property. Right? So that's exactly what we wanted. So I'm erasing this now. But you see, the point is the exact same entire proof goes through even for infinite dimensional vector spaces W, inner product spaces W, as long as V is a finite dimensional inner product space. Okay? So that's where we are going. Okay, so now let's okay, so yeah, 1 second. Okay, I think that is all correct. Okay, so this is equal to, so let's start. So first of all, the property that we have here, this is equal to W1 plus CW2 comma TV, and this of course is now an inner product in W. And now because it's all linear, so I can write this down, it's W1 comma TV plus CW2 comma TV. And now C, being in the first coordinate, will come outside. Maybe I'm jumping a step here, but this has to be C bar because it's outside inner product. Right? But now you see what is this? This is again by the same property B. So this is property B, this is by def axioms, and again by property B. All of this is in W. Again by property B, this is T star W1, comma V, plus C bar times T star W2, comma V. And these are now again back inner products back in V. And now I can again take this inside and I get C. And I can add them up, and therefore it is T star W1 plus C times T star W2, because the C bar again goes inside, whole thing comma V. Okay? Great. So that's what, so we have this original star, this expression equals this expression against all v. So therefore by homework, again I can write down this minus this comma v equals 0, and therefore by homework, I am again skipping that step. By now you have seen this many times. T star W1, sorry, W1 plus CW2 is equal to T star of W1 plus C times T star of W2 for all, for all W1 and W2 in W and C in the scalar. And that is the exact, that's what we needed. This is exactly the point that T star is linear. Oh. Here. Okay, great. So that ends the proposition. Okay, so now we understand that for every possibly rectangular map from a finite dimensional inner product space to any arbitrary inner product space, if you have a linear map, then there exists a T star backwards. I did not use the W as finite dimensional. Now I will. Okay, so now let me say adjoint of matrix versus matrix of adjoint. Where should I say it? Maybe I'll say it here. So we understand that there exists. I should say definition. I don't know if I said it here or not. Definition. Ideally, should have said it maybe even earlier. T star from W to V is called the adjoint of T. Obviously, that is the name. So now the next chapter, as I said, is so you have the adjoint. You can take some basis, and with respect to the basis, you can write down the matrix of the adjoint. It turns out that that is equal to the adjoint of the matrix, right? So that's what we want to say. So maybe the title should be matrix of adjoint equals adjoint of matrix. Okay, so adjoint of what? Of some linear map P. Matrix of what? Of some linear map P. This is the title of the section of the theorem. This is basically the theorem. So let me write down the theorem now. Yeah. Okay, so the theorem. So now I need, okay, I have erased that, but now what I do need is both of these inner product spaces need to now be finite dimensional. Okay, so oops. Okay, so theorem. Okay, so say, and again I will use V for the inner product in V, and W are both finite dimensional. And again, I don't care if it's R or C. The reason I keep saying F is eventually there will be a result where I will talk about F equals R and not C. Okay, that's going to be good. But we will do that in a minute, later in the lecture. Okay? Are finite dimensional, and I want ordered orthonormal basis. So I like, instead of saying only the orthonormal basis for V and only saying W equals V, let's take orthonormal basis for V and W with orthonormal ordered basis. Let's call it, I think I call it BB and, or I just call it B and B prime. Why did I call it B and B prime? Okay, why not? So B equals V1, Vn, and B prime equals W1, Wm respectively. So I have a finite and n-dimensional vector space with ordered basis v1, v2, vn, which are orthonormal, and an m-dimensional vector space with ordered basis w1 through wn, which are also separately orthonormal. Okay, in W, and these are orthonormal in V. Now, if you now given any T linear map between V and W, first of all, because V is finite dimensional, I know that I have an adjoint map T star. So I can talk about the matrix of T star. So T star goes from W to V, meaning I should have B first and B prime next. This is a n cross m matrix. On the other side, I have the m cross n matrix. Yes. And the claim is that these two matrices are related. How are they related? Take the transpose and take the conjugate, and that's what it is. Of course, you know what this. You would know. We know this result. We are expecting this result, but that's the answer. And now, because of this, I need to give you a definition. So, in fact, this matrix, the matrix of the adjoint, is called the adjoint of this matrix. So, definition. And now this definition makes sense. Given any matrix of size m cross n, this is m cross n, right? This is m and then n, this is n and then n. So given a matrix A belongs to C to the m cross n, meaning this matrix, define its adjoint to be A star, just like T star, which is defined to be A transpose bar. Equivalently, it is the same as first taking bar and then taking transpose, and of course, this belongs to C to the n cross n. Okay, so that is the adjoint of a matrix, and that justifies the title of this theorem or section or whatever. Okay, very good. So now I think, so now we want to prove this theorem. The theorem is going to be proved using some kind of a digression, or what I will just call it a lemma. So I'll call it two lemmas. The proof uses two lemmas. Two intermediate lemmas. So let's start by writing down those lemmas. Right? So lemma 1 and lemma 2. Okay. That's lemma 1. I have a lemma 1 is very simple. It says that look, I have an orthonormal basis of V, and again, of V. V is a finite dimensional inner product space. In particular, it's a finite dimensional vector space. And so, given an ordered basis of V, you have the dual basis in the dual space. But the dual space is isomorphic to V. Remember that phi map. So therefore, anyway, the point is this. So we want to calculate the dual basis of an ordered orthonormal basis of a finite dimensional inner product space. So lemma 1, if V, I won't put a V because there's only one space here, a V subscript here, has orthonormal ordered basis, V1, V equals V1, Vn. This is an ordered orthogonal basis. It is finite, therefore V is finite dimensional. Then B, let's call it V star, which is, let me look at these elements. Phi of V1, phi of Vn. This is just the same as saying V1, this element here. This is the same as saying Vn, and this element here. Look at these. These are n different functionals. The claim is that these form the exact same dual basis. Is the dual basis the dual basis? There's a unique one, obviously, in V star. to the basis B. Okay, so proof, this is very simple. This may even fit in here. How do you show that something is a dual basis? You evaluate the ith dual basis element against the jth basis element and check you get delta ij. You either get 1 if I equal to j or 0 otherwise. And so let's check. So phi of vi applied to vj is precisely vi against vj. Oops. And this is indeed delta ij for all ij. That's the dual basis. That is just trivial. Lemma 2 is the main thing, which again is the digression that we take. Yes, let's take a digression to understand how you compute coordinates of matrices. I mean, we know this already, but now with this new perspective. Okay, so lemma 2. Okay, lemma 2 is a slightly trickier one. Suppose I have, okay, so I have these same, I have the same B and W and B and B prime above. So B, W, B, B prime as in the theorem. So they are both finite dimensional, B and W. These two bases are both finite and orthonormal inside their spans. Okay, maybe even T and T. So then given T, a linear map, let's write down the T B prime B. Let's write down the ijth entry of this. This turns out to be equal to, okay, so it is equal to T Vj and then evaluate against Wi. This is true for all ij, of course. That is the claim. Now, okay, and here, of course, because this is W, so this must be the right inner product in W. Okay, yes, great. So I should write the W here. Okay, so let's see. How does one prove this? How does one understand the coordinates of a matrix? So proof. In general, so over general fields, not just R or C. If you have such a T, then how do you do this? If phi 1, phi m is the dual basis. Sorry, so okay. Let me first just write down what is T. If let me say A equals Aij equals T B prime B. So these B prime B are also arbitrary bases. They need not be they cannot be orthonormal, for example, unless the field is R or C. It's a very general thing. If A equals Aij, then sorry, 1 second. So then what do you do? You say that T Vj. Sorry, then, let's just say Aij is unique over the fields. This is defined uniquely here. If you calculate T Vj, then that is equal to summation Aij Wi in W. This is all these calculations are happening in W. But now, how do you calculate from this? How do you extract one element from this? Well, for that, what you need to do is you need to take the dual basis to the W's. So if phi 1, phi m is equal to dual ordered basis to the in W star, it is dual to B prime. Then what do we get? Then we see that clearly what this means is you evaluate that phi I on both sides and you get phi I of TVJ is equal to, but over here when you evaluate phi I, every other I prime, Wi prime is going to be 0. If this is a dual basis. What remains is exactly Wi, for which you get 1, times the scalar Aij, because it's a linear map. And so what we get exactly is the Aijs. So that is how you define the Aijs. Then phi I of T, sorry, of this is not an inner product, there is no inner product here. Tvj equals Aij. Already you say phi I of RHS and then and this is true for all I less equals m and j less equals m. So this is how you calculate Aij. Aij is exactly the dual basis to the W's evaluated at T of Vj. Now here you see, now basically that's exactly what we have here. Because by lemma 1, by this lemma 1, the dual basis to the Wi's is the inner product against Wi's. So now, so returning to the proof, so returning to the proof. So now what do we want? We want this statement. We want to understand the left hand side here. This is P. So now our elements are now our V and W are inner product spaces. These are orthonormal bases. This is like Aij is equal to phi I of Tvj. So far nothing is changed. This is from lemma. This is from above. And now I use lemma 1. Lemma 1 says that the phi I, the dual basis, is exactly capital phi of W. But what is capital phi? By definition, that just means inner product against this phi. And the inner product must be in W. Okay, so that is exactly the proof. Better. Okay. So that's the end of the proof of the lemmas. Now, using lemma 2, this is all that we need. This is really what we need. We will now prove the theorem. The theorem was that the adjoint, so the matrix of the adjoint with respect to orthonormal bases, and remember, these matrices are rectangular, they don't need to be square. The matrix of the adjoint is exactly the adjoint of the matrix. So let us see. So proof of theorem. This is also fairly standard now. This is just straightforward. So let's evaluate this at all j. So give for all 1 less equals I less equals m and 1 less equals j less equals n. Let me look at P star. This was supposed to go from W to V. That should put B here and B prime here. And then let's look at the J ith entry. So I will keep indexing the elements of B by Vj and J and B prime, which is Wi by I. Okay, so how do you do this? This is exactly, it is, so your T star goes from W to V. That means I have to take the ith basis of, so I have to take the dual basis, the ith dual basis of V. So the Ji, so J dual basis of V evaluated at T star Wi. I think that's correct. Yeah, that's right. So what is this? This, as we already saw, this is by lemma 1. I'll just call it L1. This is Vj, T star Wi. This, of course, is in, the inner product is in V. Okay, great. Yeah. And now if you want, no. Yeah. So first of all, this T star business, and you can move the T star to this side. So this is the theorem of T star. So above, theorem above, this is T Vj, then Wi. Great. And now, of course, I can swap the two terms and take a conjugate. So it's Wi, Tvj, conjugate. And what is this? Well, this is exactly, look, here now is the ith. So let me maybe say that again. Phi of wi applied to tvj, and the whole thing is taken as conjugate. But what is phi of wi? The dual basis of w applied to tvj. That is exactly where lemma 2. So this is lemma 2 here. And it's this thing. And this one here again is lemma 1. And now I will use lemma 2 to go back again. So basically we came up till this point, just conjugated, and then went back in the exact same reverse direction. And this is equal to t b prime b, of course ij, because I and j, and then there's also a bar. But now the ith entry of any matrix is the jith entry of the conjugate. So I take transpose, I take conjugate, and then I can take gi. So look, what we start? We started with the gi entry of this matrix. We ended up with the gi entry of this matrix, and both matrices are the same size, therefore they are the same. And this is because the point this is true for all I and all j. Therefore, this is the same. Okay, so that ends the theorem, and therefore, as I said, you have this property of adjoint matrices that if you take a linear transformation with orthogonal bases, and it has a matrix A, then against the same basis, the adjoint of that linear transformation has the matrix A bar transpose or A transpose bar. Okay, so that is that. Now let us come to some basic properties of adjoints, and these hold for rectangular matrices, not just square ones. And then we get to the hump. And then there is some extra new part, which is why I'm doing all this in rectangular setting also. Okay, so basic properties of adjoints. This is very standard. Oops. I'll just call it basic properties. Okay, I should obviously. So let's see. Proposition. Say B is an inner product space with non B, and W is an inner product space with inner product W here, are finite dimensional. Oops. These are finite dimensional vector spaces, or inner product spaces. Oh, and that's what we want to say. Okay, then we just say so T plus T prime. So suppose I have, okay, the point is if T and T prime, I also want one more space actually. Sorry. There's a third space I also want, X, let's say. X. All these are finite dimensional. Once again, over either the real numbers or the complex numbers. Okay. Now then, T plus T prime, if you take the two linear operators and then add them up and take the adjoint, the adjoint of the sum equals the sum of the adjoints. For all linear maps from B to W. Same way, the scalar multiple behaves the same way with a slight twist. Because you are taking the conjugate transpose, you would get C bar. So this time the C is a scalar and the T is of course linear. Okay, the third is that composition behaves well. And now because I'm doing rectangular matrices or whatever, that you have to be a little bit more. Yeah, that's the reason why I needed the X basically. So I say U composed with T star. So if I first apply t to go from v to w, and then apply u to go from w to x, and then take the adjoints, this is a map from x to v. Well, then you can first apply u star to go from x to w backwards, and then apply t star to go from w to v backwards, and you get from x to v for all t as above, and u from w to x. Okay, and then the fourth one is that t star star equals t, again for all p in VW. Maybe I should just have used p in then VW upstairs, but anyway. Okay, so these are the four properties. The proof is very simple. Well, not very simple, but yeah. The proof says they just use them as, just either work with, because of the theorem above, either work with an orthonormal basis for V, W, and X, in which case you can reduce everything here to the case of matrices. And then these are obvious to check. These properties of adjoints are obvious for matrices, conjugate transpose. Or you can work direct. So let me just say that's a proof. So proof either work with matrices via fixed orthonormal bases, via fixing ordered orthonormal bases for all of them, ordered orthonormal bases so the V, W, and X are all finite dimensional. So, and let me give you an example. So, for example, the fourth property becomes, right? So, you would say A is the matrix, then A star star is what? It is A transpose bar. I can also take bar transpose because it's the same thing. And this is just, so two bars in a row is just doing nothing. So, it's A transpose, then do nothing, and then take transpose, and that is just A. So, that is one way to prove. The other way is to, do the other way is either do this or work directly using the defining property of T. Like P, V, comma, W is V, comma, T, this property here. This equals this. Work with this property and make it work. So, or let me show you the question part 3. So, I've just proved 4 for you. Or work directly. Let me prove property 3 for you. Yeah. So what does 3 say? So you start with 3. U compose T star. How do you prove that this is equal to this as transformation? Two transformations are equal if and only if they act the same way on every input vector. And here the input vector would belong to X, I guess, right? Because U star goes from W to X, U star goes from X to W. So start with the vector from X, capital X, apply these 4 transformations and check that you get the same answer in V. Now, how do you check that you get the same answer in V? If the difference must be 0, how do you check that the vector is 0? If and only the evaluation against everything else is 0. So take an arbitrary X in X and a V in V. So for all X in X and V in V, we compute. We look at U compose T, whole thing star applied to X, and I want to check that against any arbitrary vector V, so everything against V, you get the same answer. Okay, so let's work it out. So first of all, a star, the defining property of star is that you can take it to the other side. So I get X, comma, U composed T of V. And now the inner product is in X, of course. But now what is this? This is just U of T of V. So this is just X and U of T of V. This is just nothing. Sorry. X. But now, see, U is being applied, so I can bring back a U. So U star of X and T of V. And now both sides belong to W. So now the inner product is in W. Okay? And that's why I keep writing down these names here. So you can be very precise. And now T is applied, so I can take T over to the other side as well. So T star of U star of X, comma V. And so look, I started with some vector and I got to the next vector. So I got to a different vector applied to V, and therefore what we get is that by homework, say homework 12, U composed with T star of X equals T star composed with U star of X. And because this vector is exactly this vector here for all X in X. That finishes the proof of 3, and similarly you can prove everything else as well. So that is why these basic properties are true. Okay, so now that the basic properties are proved, I mean, it's really simple, but yeah, just note down definitions. Here is the new part. So here is something that is sort of new. Remember, so let me first write down a heading. So much earlier, long ago in this course, we had said that given any field and any two vector spaces V to W and any linear map between from T from V to W, there exists a transpose linear map. I think I call it either the adjoint or the transpose. If I call it the adjoint, I apologize. I should have called it only the transpose. There exists a transpose linear map from W star to V star, not from W to V. The adjoint goes from W to V. But the transpose goes from W star to V star over any field. There was no reason, no inner product lurking around. It turns out that if your V and W are finite dimensional, let's say vector spaces, I think they both need to be finite dimensional. Yeah. And so the field is R or C, V and W are finite dimensional vector spaces, then there is a connection. Actually, it's not, and specifically, this is where I need the connection from R. And I will show you why we want real numbers and not complex numbers. It is because that capital phi map is not a linear map. It is a conjugate linear map, and that's a different thing from a linear map. So since we are working in the category of vector spaces and linear maps over the ground field, we want to look at only maps which are linear, and the maps phi get crucially used in what I'm going to tell you. But phi is not linear, it is conjugate linear if the field is complex. So we don't discuss that case, we only discuss the real case. Okay. The connection between the transpose and adjoint for finite dimensional technically it should be for linear maps between finite dimensional, but whatever, R vector spaces. So here I don't, sorry, R inner product spaces. That's the finite dimensional inner product. There it is. R inner I don't have space to write this, so let's write down smaller font. Fine. R inner product spaces. That is what we want to talk about. Okay. So then as I said, this is sort of new. Okay, so like last year I did not use this for sure. Okay, so let me first remind you by recalling all the things that we have said. Recall. So what was this transpose business? Let's recall what the transpose was. So over any field, so given a linear map, so again that means that you are in the category of vector spaces and linear morphisms between them. I'm not saying the vector space is finite dimensional. Okay, so recall this thing. Given this thing, there exists a unique linear map. So just like the adjoint for finite dimensional inner product spaces, for any vector spaces over any field, there exists a unique P star belongs to lin of W star to V star. given by the following. Something very similar to the adjoint equation. Sorry, this is the mistake I'm keeping on making. This is the T transpose. Okay. We want to talk about the transpose here. The adjoint was already defined. So the transpose given by or satisfying the equation T transpose of some inner. So this is an element of W star. So T transpose takes W star to V star. So how do you define this? This must be an element of V star, and indeed it is by defining it to act on V. Is defined to be exactly T. So first take V, act on it by phi. Phi is an element from, sorry, other way around. So first take V and act on it by T. Now T goes from V to W, therefore this is an element of W. This takes W to scalars, so evaluate that. That is the definition of T transpose applied to a linear functional. You can check that what you get here is a linear functional, and therefore that defines T transpose of phi. Okay, so that is the definition of the conjugate, and we also saw that. So this was let's say so given this T, if we are also given ordered bases of V and W, then with respect to the dual bases, you get the conjugate, the transpose matrix. So if V, VW are ordered bases, now the field is not R or C, so I can't say orthogonal or something like that. Ordered bases of V and W respectively, and V star, VW star are the respective dual bases. I'll just say are their respective dual bases. Right? So if BV and BW are ordered bases of V and W respectively, and BV star, BW star, which are in B star and W star, the dual bases are the respective dual bases, then what happens? Then what I want to say is that look at the matrices. Then the matrix of T transpose with respect to B. So T transpose takes W star to V star. So this should be V star, VW star. How is it related to the matrix of T with respect to BW, VV? The answer is it is precisely the transpose of this matrix. That is the theorem. That was the theorem, right? So I didn't out of it. T, BW, BV, transpose. Okay, that was the result. So now the question is, so now suppose now say V and W are finite, were these finite dimensional? No, but now let's say they are finite dimensional inner product spaces. Over F, which is equal to, as I said, I cannot take C, and you will see very soon why. Again, okay. Also suppose that BV and BW are orthonormal bases. Okay, Then on the one hand, of course, you have the transpose map because you have it in complete generality. But on the other hand, because of this, you also have the adjoint map. The question is, how does T transpose belongs to lim of W star and V star relate to the T star? Okay, that is one question. And the second question is, what about the matrices? Of course, if the field is real numbers, then you can imagine that, okay, the answer to the second question is going to be obvious. Two. What about the matrices themselves? So what about the connection, the other things which are matrix T transpose, B V star, B W star versus the matrix of T itself, T adjoint. So what about these two maps? How are they? And this, the answer to the second question is obvious because this is equal to answer to 2. It's obvious. This is equal to the transpose of this matrix. And this is equal to the conjugate transpose of the same matrix. However, over real numbers, this is equal because there is no conjugation. The answer to the second question is obvious. So what we want is really to answer the first question. And we are going to answer it in such a way that it also implies the second question. Second answer, this answer. Okay? So here is the theorem. Yeah, of course. So yeah, so this here should be the dual bases, right? We said, yeah, these are the dual bases. So these should be orthonormal and these should be dual. So yes, fine. Okay, so let me write down the theorem and prove it. Yeah. Okay. Let's see what I can do. Yes, so let's see how much I can do today. Maybe I may not be able to get to the spectral theorem, but we will see. There is one more class in the course, so that's the last classes with the spectral theorem. Okay, fine. Let's continue. Okay, so theorem. Which will answer the first and the second question. We already know the second question, but fine. Okay, so maybe I should first explain to you what's going on here. Okay, so given a T from V to W, so you have a T from V to W, you have the following maps. On the one hand, you have W to V. This is T star. From V, you also have a map to V star. This is the map phi V, which takes any vector V to the inner product against V. From W to W star, you have the same map phi W. And then from W star to V star, you have the transpose map. And so, of course, you can ask, if I start with an arbitrary element here, I first apply T star and then apply phi V, I get to an element here. Or I apply phi W and then I apply T transpose and I get to some other element here. Do I, by these two paths, get to the same element? That's my question. Well, also, that's the same as saying, look, these are vector space isomorphisms. Not vector space, but these are, and oh yeah, now they are. Now since the field is real, and this is why I wanted the field to be real, so all these maps are linear. Since F is R, all four maps are linear, meaning they are morphisms, right, in the correct category. So in particular, you see this phi d and phi w are isomorphisms because they are vector space isomorphisms. So instead of going T transpose, I could put the inverse of this phi w, then apply T star, then apply phi w. Or instead of going T star, I can first go phi w, then T transpose, then the inverse of phi. The question is again, is T star equal to the composite of these three maps? Do you get the same answer? So really the question is whether it's called, the formal way to say it is to ask if this square commutes. Okay, that's the standard way, and then you write down a crispy arrow inside. So theorem, when the field is real, so all four maps are actual morphisms in the correct category. The theorem says that yes, it does commute. And that's why the star and the transpose, that's how the star and the transpose are related, which is what we were trying to see. Okay, so fixed finite dimensional in the product spaces. Let me specify all the players in the game. V W finite dimensional, and this time I want over the real numbers, not over F is R or C. This is the one result why I've been keeping on saying F, because this is not just F is R or C, this is F. And a map T which is linear. Fix this map, fix the vector spaces. Okay, then that's square curve. So basically then you can write it either way. You can say that T transpose is first you apply phi W inverse, then you compose with T star, then you compose with phi V. Or equivalently, I could say T star is phi. Now first I apply phi V. No, first I apply phi W, then I apply T transpose, and then I apply phi V inverse. Or equivalently, the above square commutes. What does it mean to say the square commutes? In other words, composing one way and composing the other way is the same thing. If you first apply T star and then apply phi V, then this is the same map as first applying phi W and then applying T transpose, and this is true on all of W. That's what it means to say that the square commutes. And the second one is of course that. So now we can write down the matrices. Right? I have a set of fixed orthonormal bases. So look, this one comes with the basis VW. This one with the VV, VW star, VV star. So with respect to those orthonormal bases and their dual bases, I have matrices. There's a matrix of this, there's a matrix of this, there are these matrices. So we want to claim that these two matrices are equal. Well, it's equal if you can somehow say that, these two matrices behave nicely. I can take matrices on both sides. It turns out, guess what, the matrix of this guy with respect to BV and VV star is the identity matrix. And the matrix of this guy is the identity matrix. So of course, if these two are identity matrices, then these two matrices have to be equal. And that's why it's true. Okay. So now, again, fixing these bases. So 2. Just move to a different pen. With BV, BW orthonormal, and BV star, BW star, their dual bases. What you can say is I can look at phi, the matrix of phi. Phi goes from V to V star, so I can say BV star BV is the identity matrix. And this is also the identity matrix, similarly for phi W. I'm not saying equals because the identity matrices may have different sizes. N and M, for example. For the matrix of IW. In particular, now you can just plug in the take matrices over here and you get to the matrix of T star and the matrix of T transpose are the same. Implies by one. So by the first part, it's obvious that the matrix of T star. Now T star goes from W to V. So I have to say BV BW. This is equal as a rectangular matrix. These are rectangular matrices to T transpose. T transpose goes from W star to V star. So I have to say V star, BW star. Did I do something wrong? Oh god. Okay, first of all, I did something. Yes. T transpose VV star to VW star, T star VV to VW. Yeah, that's right. So the second part is sort of obvious the moment I prove this equation, which we will now. It takes like 1 second to prove. So. But first, let's prove part 1 and then we will just come to part 2. Or maybe, fine, let me just do part 2 right here. Yes, let's prove part 2 right here. So proof of 2. So remember I proved those two lemmas today, lemma 1, lemma 2. So by lemma 1, the dual basis. Lemma 1 above, the dual basis is exactly that. Right? So to the Vi, Vj is phi Vj. Phi V of Vj, sorry. But what does that mean? It means that Vj is taken to phi V of Vj. The first vector is taken to the first vector, the second vector is taken to the second vector. That means the 1 1th entry, the 2 2th entry, and so on are all non-zero, are equal to 1. All the other entries are 0. And so this is just there. From this statement alone, you get that it's the identity matrix. So this implies this. This implies this fact. And the moment this implies this fact, this is just trivial by taking matrices on both sides. Identity times something is something times identity. So these two must be equal. Okay, so now what remains to do is the proof of part 1. That is what we want to really show. That there is this conceptual reason why the two matrices are equal. They are equal because this diagram commutes. Okay. The proof of 1. Okay, so the proof of 1 is as follows. Yeah, so, and the proof of 1 is exactly, again, you can probably do some kind of a strange take orthonormal basis and do matrix calculations. But the simpler way, the simplest way is to just use that same inner product identity, where you can take the T or T star or T transpose to the other side. Right? So T transpose has an identity where you can take it to the other side as T. And T star has an identity with inner products. T transpose has with functionals. T star has with inner products, where you can take it to the other side. Let's use both of them and check. So it's enough to check the diagram commutes because all these maps are invertible. So what happens? Okay, maybe I should start by saying why are these two equations the same? Why is it equivalent? It's equivalent because suppose I know the first equation, then I can pre-compose by the inverse of this. So I can multiply both sides, if you will, by the inverse of this guy. So I get phi V inverse times T transpose. And also I can multiply the right hand post multiply by the phi W. So on the left hand side, this would cancel, this would cancel. On the right hand side. On the left hand side, I would get phi V inverse T transpose phi W. And that is exactly this expression. Similarly, if I take this second equation and multiply by phi V inverse on the right, on the left, then I get that this guy here is equal to phi V times T star. Okay, so it's enough to show this square from you. So let's just say this is equation star. So proof of 1 enough to show star. Now, where are these two elements sitting? These two are linear maps from W to V star, right? So how do I show that a map from W to V star equals another map from W to V star? I have to show that at every element of W, you get the same linear functional in V star, meaning at every element of W and evaluated the functionals at every element in V, you get the same scalar. That's how you would show, right? I.e., for all W in W and V in V, we want to show that the left hand side, phi V of T star of W, this is a linear functional in V star, so I evaluate it at V. Okay, so I want to show that this functional at every W equals T transpose of phi W of W. I want to show these two are equal as functionals, as elements of V star. How do you show that two functions are equal? They have to be equal at every input. So we'll take the input as any arbitrary V. You have to show that this is true for all W and all. Why is this true? If you want to show this, and the proof is that, let's start with, let's say, the left hand side. So now what T star W, T is a map from V to W, so T star is a map from W to V. So this is an element of V. And I'm taking phi V of that. So I'm evaluating against this element. Right? So this left hand side equals T star of W, inner product against this. Inner product, of course, is in V. I'm just doing it step by step, following the definition, nothing else. Okay, now because of the property of T star, I can adjoint property, I can take W and TV. Now the inner product is in W. Okay, that is the left hand side. Similarly, let's look at the right hand side. This is T transpose phi W of this. Now this thing is an element of W star. We know the definition of T transpose. T transpose at any element of W star applied to V is that element applied to T of V. This is the definition of T transpose. But what is this phi W of W? Phi W of W is exactly the inner product against W, and that is being applied to T. And so look, the left hand side and the right hand side are the same. For every vector V, therefore, without the V, the two sides are equal as functionals in V star for every vector W, and therefore we are done. So maybe I'll write that out, because maybe once in your life you should see this. No? Implies, what does happen here? Implies phi V of T star of W. Maybe I'll write it slightly differently. I'll use the composed notation, composing notation. Phi V composed T star of W equals T transpose composed phi W of W as elements in the star, in the functional space, for all W. But now that again means that if you have two functions which are equal at all points, then you already we have proved part 2, and now we have proved part 1, and so the theorem is true. Okay. So finally now, once this is done, we can now move on to orthogonal and unitary maps, and then orthogonal and unitary matrices. After that, we will move on to normal matrices and then talk about the spectral theorem. But probably not today. So today I want to finish orthogonal and unitary maps. Maps is easy, then the matrices also. Actually, it should be unitary and orthogonal, but fine. These are linear transformations, first of all. And then when we fix the standard basis and so on, we will take matrices. Okay, so the question really is, again, yeah, this is good enough for the question. And then examples and the theorem will go there. Yeah, I'm going to switch pens. Okay, let's see. So, question. The question is, suppose I'm given an inner product space, okay? Which linear maps preserve norms in this inner product? Meaning the norm of the output is the norm of the input always. Or for example, which ones preserve norms and angles? The angle between two vectors is equal to the angle between two output vectors. So given V finite dimensional, let's say just given V, right? Given V in inner product space, and this time again this is over R or C. Which linear maps T from V to V preserve norms or angles, preserve norms or inner product. Oops, I don't know what happened here, but this is product. If you can't read it, preserve the norm / inner product. So what does that mean? It means that if you look at the IE, the norm of TV equals the norm of V for all V, or the inner product of TV and TW equals the inner product of V and W for all V and W in V. Which linear map satisfy this property? Okay, and so let me first give you two examples in the plane, in the usual R2 plane, and then let us look at the theorem. Okay, so F equals R, V is R2, the standard plane, and a T is either rotation by some angle I don't care which angle, but the point is that once you rotate, the length doesn't change. And you can even check that the inner product, the dot products don't change either. Okay? Another way is reflection about y equals mx, or let's say m is in R, or m could even be infinite in the y-axis. But yeah, so that's what it is. Either way, the reflecting a vector around some hyperplane, around some axis in the plane, around some mirror, does not change the length of the vector, nor does it change inner products. One can check. And similarly, rotation also doesn't change it either. Okay, so these are two examples. Fine. Okay, are both examples of such maps. Okay, so now with this, but what is the general answer? That is the question. And the answer is that it's given by something called orthogonal or unitary maps. So theorem. Yeah, so let's write down the theorem. Great. Oops. Maybe a better pen. Let's see. Always need pens. Fine. So say T goes from V in a product space to itself. I'm not assuming finite dimension, okay? I'm not assuming finite dimensional. The following are equivalent. Oh, sorry, is linear, of course. The following are equivalent. One, the norms are preserved. TV equals V for all V in V. The second is T VTW, inner product is preserved. W for all V and W in W. In V, sorry, not W. There is no W now, it's only V. And the third one is the condition, the actual equivalent condition, if you will. T star times T. So look at T star. Now you know that in any inner product space, oh, I think I will need finite dimensional. Right? How do I know T star otherwise? Is and V finite dimensional. Sorry, I assume there is linear. I won't write that down. And dim V is less than infinity. T star composed with T is identity map, which is if and only if T composed with T star is identity map. And that is just because, basically these two transformations are invertible, then the left inverse equals the right inverse in a finite dimensional space. That's fine. I need to probably write something here. And be finite dimensional. Okay, so this is the theorem. Proof. Let's start proving it. Some of the proofs are trivial. Some of them are very interesting. Proof. So let's see. 2 implies 1. 2 implies 1 is obvious. If you know you preserve inner products, just set W to be V. What do you get here? You get the square of the norm on this side and the square of the norm on this side. But these two numbers are non-negative, so take the square roots and you are done. So set W equals V. I will just say that. Set W equals V. And you just get 1 for free. I mean, take square roots, but I won't say that. Okay, 1 implies 2 is the interesting part. This is where we learn a new couple of identities. And okay, 1 implies 2. So we use the polarization identities. Polarization identities over R or C. See, here I did not assume that the field was the real numbers, right? So the polarization identity over R or C. So what are these identities and how do they help us to prove 2 assuming 1? And again, of course, I should add, a statement in norms is not that nice. So of course, what you should be doing is a statement with the norm squares. Right? So we will of course do that. We will square both sides and we will use that to prove statement 2. Okay, I think that should probably change to So I'm proving 1 implies 2. Okay, but first, these identities are themselves useful or nice to know in their own right, without just being tools towards the proof. Okay, so for let's say F equals R. This is a homework problem. So initially I was going to give you the complex one for the homework, but roughly speaking, the calculation is exactly the same thing as this real case. So and it's the last week and I think everybody must be tired. So let's just do the real case of the homework. If you take the inner product, so what was the point of 2 implies 1? It was that you can write down the norm in terms of the inner product. And you can take TV, TV and then take square root and you get the norm. Interestingly, the polarization identity tells us how to go the other way. You can write down the inner product in terms of the norm. And that's what we are doing. So the inner product over a real vector space, I crucially need the real vector space here, is 1/4 of the norm of V plus W square minus the norm of V minus W square. So check. This is the homework. You have to check that this works out. Okay. But now once you have this, using this, we are done. Because now if we want to prove 1 implies 2, so if 1 holds, then you start from V comma W. You first write this down. Sorry, you start with You want to TV TW is VW. So you start with TV comma TW. Maybe I'll just do it here. So TV comma TW. So first of all, it is 1/4 of TV plus TW square minus TV minus TW square, because this identity holds for TV and TW. In the I should have pointed out. Okay, everything here is from V. So all these inner products are in V. There is no vector space W. Okay, great. Yeah, but now of course this is by linearity. This is 1/4 of norm of T of V plus W square minus the norm of T of V minus W square. And now here is where I use property 1. Property 1 says that the norm of T applied to anything is the norm of that thing. So by 1, it's 1/4 of V plus W square minus V minus W square at the same token again. But that is exactly equal to V. So you see, just by using that identity at the top of the board, this calculation becomes very easy. You can express the inner product in terms of norms and then just make things work out. So now we need to answer what about the complex case. Well, it turns out the complex case, this will not quite work. So what do you do? Well, there is a complex polarization identity, and that's what I will now tell you. First, I need to keep the barrier. Okay, so complex polarization. If you want, you can verify this on yourself, but it's the same kind of identity. So again, you can write down VW over a complex space. So first of all, you still write down 1/4, but now the expression is fancier. You get V plus W square. This part doesn't change. Minus V minus W square. This part also doesn't change. And then there are two extra terms, which of course are obviously new. Minus I times V plus IW square. I is of course the square root of -1 plus I times V minus IW square. That's right. And so once you have this, then you can carry out the same game like this. And so that's how you show that 1 implies 2. Okay, so I'm not going to prove this part. You can obviously deduce it for yourselves. So 1 and 2 are done. Now 2 and 3. Okay, so 2 implies 3, let's say. Yeah, why not? Now apparently 3 implies 2 is shorter, so let's do 3 implies 2. 1 second. Okay, maybe we will stop after this and I will start with unitary and orthogonal matrices a little bit. Fine, then let me go a little more. Yes, so. Okay, so 3 implies 2. So I know 3, I want to do 2. Let's start with TV comma TW. But now by the property of the T star, I can take the T on the other side and I get that it's T star T of V comma W. But T star T is identity and therefore I write down V comma W. Done. 2 implies 3. Now I know that equation 2 holds and I want to prove that T star T equals identity. So let's start with T star. So let's start with T star T of V comma W just for fun. And now note, I want to prove that this is V comma W. But first of all, because there's a T star, I can take it to the other side. I get TV comma TW. And now by property 2, this was property 3 here. By property 2 here, I can get this is V comma W. And now this is true for all W. Because it's true for all W, that means T star T of V minus V is perpendicular, is orthogonal to all vectors W in V. So by the homework problem, T star TD equals V for all V in V. But which linear transformation T star T can take V to V? That's precisely that's the definition of being the identity. So that's pretty much the end of the proof. Okay. And now one more small thing. Okay, so now therefore, let me therefore end with the definitions of unitary and orthogonal. Basically, this is what a unitary map is. It's a map that satisfies this theorem. This theorem. Definition: a map that satisfies these equivalent conditions is said to be unitary. A map T from V inner product space to itself, as in the previous theorem, is said to be unitary if F is the complex numbers and orthogonal if F is the real numbers. These are what are unitary and orthogonal maps. Oops, sorry. Okay, so now, so basically it just means that T star T equals identity. Effectively, what it really means is T star T equals identity. Now, because this is true, you can go from maps to matrices. So let me say a little more and then we can stop. Yes. I will finish the unitary and orthogonal matrices and then we will stop. We talked about linear transformations which are of that kind. Let's talk about matrices that are of that kind. So definition. I need a new pen or something. Let's see. A matrix A is C to the n cross n is unitary. So that I'm going to give you a definition which is slightly differently phrased, but it is exactly the same. If A inverse equals A star, well, if you have two matrices which multiply like this, then then that's basically what you're saying. And then B, a matrix A in Rn, not Rn cross n, sorry, on Rn is orthogonal if now I don't need to take the conjugate transpose because there is no conjugate needed. So I just take the transpose. But of course that is equal to A star as well. So every orthogonal matrix is unitary. Obviously the converse is not true. There are complex matrices which are only unitary but not orthogonal. Okay, so let's just see some. No, the third episode. Maybe I'll say the third part. Define the sets. U of n is a set of all unitary matrices A in C to the n cross n, such that A is unitary, and this contains O of n A in R to the n cross n, such that A is orthogonal. Okay, that's the these are obviously sets. They both contain the identity matrix, for instance, and so on. Anyway, so let me just say that these are precisely the unitary or orthogonal transformations. When are matrices equal to linear transformations? If you take f to the n to be the vector space, and the standard basis, the standard, in fact, orthonormal basis in this case, to be the basis. And then these are exactly that. So these are precisely the unitary or orthogonal linear maps from V to V. For V equals Fn, when F is R, then it's orthogonal. F is C, it's unitary. But of course, I'm talking about maps which are unitary or orthogonal, so they have to be with respect to some inner product space, right? So what inner product? Well, you can guess this is obviously the standard inner product with respect to the standard basis, right? It's summation Vi, Wi, or Ai bar Bi. Well, Ai and Bi are the coordinates with respect to standard basis, which is indeed orthonormal. So the point is that the basis we have, the standard basis, is not just very nice for linear algebra in general, it is also very nice for specific linear algebra for R or C because it's orthonormal. With respect to standard inner product, should we write that maybe? Yeah. To the standard inner product. With respect to the standard basis. This should also go. Okay, that's exactly what these are. And let me write down a few basic properties and we can stop for today. Basic lemma. Yeah, we'll do a couple of basic properties and stop. Think I don't have. So A is in U of n. Suppose A is unitary. For example, A is orthogonal, then A is invertible. Matrices are closed under lots of objects. So U of n and O of n are closed. So if two matrices satisfy this property, then their product satisfies the same property or the same property here. If a matrix satisfies the property here, its inverse, because remember it's invertible, its inverse satisfies the same property, and so on and so forth. So there are 3 or 4 properties. The transpose satisfies it, the conjugation satisfies it. Under I don't know, ABCD, I just say multiplication. I think then the next one is inverse, maybe. No, conjugate, transpose, and inverse. I mean, it doesn't matter which order. Undertaking conjugates, undertaking products, undertaking inverses, and undertaking transposes. Third, there are more. Yes, this one. This is the actual property. A matrix is unitary or orthogonal. I mean, 3 prime is ON. If and only if the rows or the columns form an orthonormal basis. not just a nice basis. It's invertible, so of course its rows and columns form bases of Rn or Cn. But its rows and columns form orthogonal bases. That's the nice property about an orthogonal matrix or a unitary matrix. The rows and columns are a very nice special basis. Orthogonal basis. Okay, and corresponding you have a 3 prime. For the real case, A is orthogonal, not unitary, not orthogonal. If and only if the whole same thing, orthonormal basis of R. Okay, let me quickly prove this. Sorry, it's a little bit extra, but let me quickly prove this and stop. Yeah, because this is really very little. So let's just quickly do this. It will take 2 minutes. Okay, so the first one is basically by definition. Right, the first one is because, well, A inverse A star. So that's why it's true. By definition, or you can say that, and you can also say that because A times A star is identity, therefore, that means there is a matrix, so that A times that matrix is identity. So therefore, that's the inverse. Second, well, the second part that I'm giving you here is part of your homework. So homework 12. The third part is so the 3 and 3 prime are the same. That means write either of them. Let me write 3. And we will stop. Should be enough space. Let's write down 3. So A is unitary. So let's say A, let's write down the columns of it. V1, V2, Vn. This is n cross n. So each Vi is a column vector in C to the n. Okay, fine. Now this vector is unitary. This matrix is unitary. If and only if A star A equals the identity matrix n cross n. But what is A star A? A star A, so if you multiply, so A star here, of course, is V1 star, V2 star, Vn star. This is the identity. So A star times A. Now you can multiply these out using this kind of partition matrix calculations, right? You don't need to actually understand the entries. This time, this is partition matrix kind of thing. So A star A, so this is if and only if. What is A star A? This is V1 star V1, V1 star V2, V1 star Vn, then V2 star V1, and so on till V2 star Vn, and dot all the way until Vn star V1, Vn star Vn. This matrix is A star A. So something is the identity matrix. Well, so A is unitary if and only if this matrix is the identity matrix. But then what does that mean? It means the ijth entry here is the ijth entry there. The ijth entry on the right hand side is delta ij. The ijth entry on the left is Vi star Vj. But what is Vi star Vj? In the complex inner product, the star is the first operation, so conjugate here. That's exactly this thing for all I. And the fact that this inner product equals delta ij is exactly the same as saying that they form an orthogonal basis. Of C power n. And you can of course do Rn as your unit or orthogonal matrix. This was then the columns form orthogonal basis, right? But now how about the rows? Well, the point is A is unitary, implies A transpose is unitary. A transpose is unitary implies A is unitary. So it's if and only if. It's A is unitary if and only if A transpose is unitary. If and only the columns of A transpose form an orthonormal basis of Cn, but the columns of A transpose are precisely the rows of A, up to transposing, of course. So that's all we get. So let's say A is in unitary if and only if A transpose is unitary, if and only if the columns of A transpose form an orthonormal basis. Equals orthonormal basis of Cn, but the columns of A transpose are precisely the rows of A, and up to taking transposes. Of course, each of the rows must be transposed, but that's what we want to do. Okay, so that ends this lecture. So we have now finished everything up till normal matrices. So next time, in the final lecture of the class, we will start on normal matrices, give some examples of normal matrices, then write down and prove the spectral theorem. Okay, that's it for today.